into units. Units in radiation protection. So the fundamental dose quantity, or the fundamental unit, or dose quantity, I guess we could say, is the absorbed dose, given by the symbol D. There. Absorbed dose is just the energy absorbed per unit mass. So the SI unit for absorbed dose is the gray, and it's defined as 1 gray is 1 joule per kilogram. Prior to SI units, the unit for radiation dose was the RAD, radiation absorbed dose. So 1 RAD of an absorbed dose is 100 ergs per gram. If you like ancient units, there you go, you've got your ergs. So 1 rad is 100 ergs per gram, but since 1 joule is 107 ergs and 1 kilogram is 1,000 grams, 1 gray is roughly around about 100 rads. Or 1 centigrade is 1 rad. So people doing radiotherapy will recognise this, excuse me, as a monitor unit is typically set up to be a centigrade. And that comes from the fact that not every country has switched to SI units yet. So, for example, the United States still uses rads and Watkins and all of that sort of stuff. Exposure. So, for an external radiation of a given flux, the absorbed dose is different to different parts of the body. So, if you stand in a radiation field, different parts of your body will get a different radiation flux. So, this is going to depend on the type and energy of the radiation. If it's more penetrating, less penetrating, depth within the organism or depth within you. Deeper tissues, the radiation is going to be attenuated as it passes through your body. So deeper tissues will get less dose. And also the elementary composition of the material. So, for example, if it contains, we've got this example here. So bone has a higher atomic numbered elements than soft tissue. So bone tends to absorb more radiation per unit mass, or more energy per unit mass when put in an X-ray field. Exposure, so the radiation fields to which a person is exposed is specified in exposure units, or X. The exposure unit relates to the amount of energy transferred from the radiation field to the unit mass of air. Alright, so exposure is talking about energy in air. So 1 exposure unit is 1 coulomb per kilogram of air. To convert this energy absorption per unit mass of air, so we have the charge of a single ion is 1.6 times 10 to the minus 19 coulombs. Average energy dissipated in production of an ion pair is about 34 electron volts. So this is an average energy. So approximately it's going to equal 34 gray in air for 1 exposure unit when you convert exposure to energy per unit mass. So here's an example just from the book by Semba. To calculate the absorbed energy in joules per kilogram of muscle tissue corresponding to an exposure of 1 coulomb per kilogram in air. If you go through, and we've got our masses here, or the number of atoms per gram there, and we've got electron density, which can be calculated from that, so air has a density of that, or let's assume air has a density of that for the purposes of this exercise. Obviously it's going to change with atmospheric conditions, and therefore we can approximately work out that 1 coulomb per kilogram in air will approximate to 37 joules per kilogram in muscle, so 37 gray in muscle. Other units in radiation protection are mainly the sievert. It depends upon the radiation interactions of the body. So we're going to move to sieverts. So this will be for effective dose and equivalent dose. But before we can move on to that, we'll just have a quick detour, and we'll come to that. The next few slides we're going to jump around a little bit. Alright, so first thing we need to know is a linear energy transfer. So some people will have studied this previously, some won't have. So linear energy transfer is refers to the amount of energy locally transferred to the material per unit path length of the ionising radiation. So if you're looking at a radiation coming into a material, let's say muscle, over say a centimetre, some types of radiation will deposit a lot more energy than other types of radiation. So for example, photons and electrons transfer around about approximately 0.3 keV per micron. The average energy loss per ionisation event is about 34 electron volts, approximately an average, so it's not always the case, obviously. So we can say that there's approximately 10 ionisation events per micron from photons and electrons. Now, if we have a look at a radiation which is, say, it's 1 MeV, and this could be photons, electrons, alphas, whatever. If we look at 1 MeV and we have an average of 34 electron volts per ionisation event, so 1 MeV divided by 34 electron volts will mean that for 1 MeV it should result in approximately 30,000 ionising events occurring. Compared to the dimensions of DNA, these distances of 10 ionisation events per micron, so for photons and electrons, these distances are pretty large, and so the probability of causing 2 ionisation events in one segment of a DNA cell is very small from a single X-ray. And the probability therefore of a double strand break is also small, but this increases as the radiation dose increases. So the more X-rays or more photons or more electrons that you put into a cell, you'll have more tracks, radiation tracks, and therefore you have a greater chance of causing a double break in the DNA. But there's different energy for high LET radiations, all right, like alpha particles, which has a LET of around about 200 keV per micron. In this case, 2 ionisation events can be caused by the same particle less than a nanometre apart, and I'll explain this on the next slide. Alright, so here we have which is meant to be a drawing of a cell, and we have two radiation tracks here. So we've got a low energy one up the top, oops, there we go, and a high LET one down the bottom. Yeah, let's draw a DNA track through here. Alright, I drew that wrong. Let's try another one. We have a DNA track here, or DNA strand here, and we have our little ladder. This is our DNA ladder. Excuse my bad drawing. Now, if you have a look at this low LET here, you can see that the chances of these ionisation events occurring both sort of within like this area of the DNA is a lot less than down the bottom here, where there's a much higher chance that you'll get a double strand break of DNA. So this is why high LET radiations are more damaging than low LET radiations, just because for a single radiation event or a single radiation track, there's a much higher probability that that it's going to cause a double strand break. So here's the linear energy transfer for some different types of radiation. So X-rays, gamma rays, electrons, betas, about less than 10 MeV, so it's quite low. Protons and neutrons, 10 to 100, so this varies. Neutrons vary with energy. Alpha particles greater than 175. So alpha particles deposit energy a lot closer, in a lot closer distances than, say, X-rays and gamma rays. So alpha particles become more damaging. So we can say that the damage done to a cell depends on the type of incident radiation. So we can take this further. We can we can't actually use the absorbed dose anymore because we have to know what the type of radiation was. So we have to introduce what's called a radiation weighting factor, given by WR. Now here's the radiation weighting factors given in ICRP recommendations. 1991's on this column, 2007 in this one. So there's a few changes. So in both photons, electrons, muons, the radiation weighting factor is a 1. For neutrons, there's a big energy dependence here. For protons in 1990 it was a 5, meaning that protons were considered 5 times more damaging than photons and electrons. This got revised down to 2 in 2007. Alpha particles, 20 in both cases. So alpha particles are considered to be 20 times more damaging than photons. This is also heavy nuclei, so for example carbon ions, or fission fragments as well. This is the radiation weighting factor for neutrons. So remember on the previous slide, neutrons were quite energy dependent. So this is the calculation here for neutron radiation weighting factor, which looks rather unpleasant to try and work out.